Ngalakin kadijan nyunga boja.
Okay, so let's make a start. A couple of points to mention. I had a couple of emails about there's meant to be a computer lab on Monday, but Monday's a holiday, but that's just a scheduled. That's just a scheduled lab. Okay, so if you just need to use the computers, you can go there. So you don't have to, you don't have to turn up on Monday. You shouldn't have to anyway, because you don't have any labs or anything yet to do in the computer lab, right? So don't worry about. I'll send out an email about that. Okay, so some people who are assigned to the lab on Monday said, is it on? Do we have to go? But it's just a computer lab, okay? So, and they've just block assigned a whole number of weeks, and this Monday just happens to be a public holiday. But it's not something. It's only just to give you time, exclusive time on the lab computers if you wanted it, right? So you don't need it. Okay. Okay. So we'll try and. So this first part, I know it's a bit not very definitive, but it's just an introduction on modelling and where things fit. Okay. But we'll try and get through it probably by the end of this lecture and beginning of the next one, and then we'll get on to more concrete things. Okay, so continuing on with looking at modelling in general, and electronic systems. What are the things that underpin system analysis and electronic system analysis and design? Well, I suppose we start off with things like for circuit theory. It's based on graph theory and calculus and some other maths. Okay, and then we also have physical electronics, and that's based on physics and solid state physics and quantum theory. Okay, you would have done some of that in 3014. And then we also have field theory, which we're going to look at in the second half, which is electromagnetic theory. It's based on physics and also vector calculus. Okay, and then we use all those in network or circuit theory. Okay, to make electrical circuits. Okay, and then above that we also may have other sorts of theories. Okay, to do with higher level abstractions like communications theory, signal processing control theory, and all those things go together to make electrical systems that we design to solve problems, hopefully. Okay. Okay, so when we select a model, okay, we want to model components and systems. Okay, we do it in a context. Okay, so we mentioned before. One of the contexts is what we want it for, but also the types of signals that we need to represent. Okay. Okay. So the type of signals determine the models that we need for each element. Okay, and for analog signals in particular, okay, we have a certain number of types. Okay, we have transient signals, which are due to perhaps initial conditions in circuits. Okay, some of the decaying exponentials, some of the decaying sinusoids, or the response to some stepped excitation. Okay, and then we also have a steady state response. Okay, not just to DC, but remember also to sinusoidal excitations. Okay. So in systems, you can also have other types of signals. Okay. We'll look a bit more of that. And one of the main other types of signals, but not just analog, is also that we have digital signals. Okay. Okay. In the design of most systems, we use different levels of abstractions to manage the design process. Okay, and we use models with different levels of detail for different perspectives. So the idea of having an abstraction and making a model is that we want to encapsulate the behaviour of some circuit or system. Okay, with just sufficient detail. Okay, to allow us to make useful predictions about it. Okay, or to modify it in certain ways so we know that what it's going to do. Okay, and try and remove all unnecessary details that aren't going to impact on the results. Okay, and generally after we've done some initial simplified analysis, we'll often use computer models, okay, to actually verify that, and finally we generally need to validate with some sort of prototype. Okay, abstractions may be formed by reducing the information content of a concept or an observable phenomenon, and as I said, typically only want to retain information that's relevant to a particular purpose or perspective. Okay, focus on essential core for the purpose at hand. Okay, for example, maybe just a certain frequency range, certain electrical power dissipation, etc., etc. Okay, but you always have to keep in mind there's a difference between abstraction and reality. Okay, and you make abstractions and do things, but to actually see the reality, you'll have to do experiments and do measurements. Okay. So looking at analog signals, they're linear. You have, generally we deal with linear in analog systems. You have infinite resolution of values. You use circuit theory for modelling analysis. Okay. You have frequency domain characterization. You have idealised models. Okay. Digital systems. Okay. We're interested in Boolean variables. Okay. Boolean algebra. We have well-defined precision, long-term information storage, and most important, we have all these things on repeatability and reliability. Okay, but as we'll see more in the course, you don't really have just the two worlds. All digital signals are actually analog signals in the beginning. Okay, and you'll see that. Soon we'll see that. You need to take that into account to be able to design reliable systems. Okay. For people who did 3017, you may have seen this sort of thing before. But digital systems or digital devices work by mapping some input voltage range into either 1 or 0. Okay, so if we have the input to a particular device, it will look at, for instance, the voltage between this VIL and 0 and classify that as a logic 0, and it will look at the voltage between VIH and say the maximum voltage 5 volts and class that as a logic high or 1. Okay. And the important thing is that, for instance, say this was an inverter, the actual output of the circuit, digital gate or integrated circuit, will map that particular voltage range into a more restricted voltage range. Okay, so in this case it's an inverter, we map a 1 to a 0. Okay, but we can see that the output voltage range is a smaller range than the input voltage range. Okay, and similarly for the high output, the output 1 is in a smaller voltage range than the input voltage range, which is recognised as a 1. Okay, so that gives us a noise margin. Okay, so it means that if the noise on any output signal is less than this particular margin, okay, then the following circuit's always going to interpret it correctly, okay, as a 1 or a 0. Okay, so that's why digital signals or digital systems are so reliable. That's why you can have thousands or millions of transactions occurring in perhaps your iPhone every second, and you don't have any faults. Okay, because you have this particular noise margin. So as long as noise is bounded to less than this, every transaction between integrated circuit or gates on a particular chip will always have the correct result. Okay, because the inputs are mapped to some smaller region. Okay. However, we'll see, especially later in the course, we'll talk about digital system signal integrity. Okay, so we may have some gate or integrated circuit that drives has some outputs, okay, and outputs some digital signal that goes from, say, 0 to 1, okay, then that goes along a transmission line to a destination, okay. So first of all, the transmission line always introduces a delay as expected, but it may introduce other effects, okay, depending on how the line is loaded and how it's driven, okay. So it may cause some significant distortion like ringing or some staggered delay, okay. And that affects the noise margin, okay, seen by digital inputs of the system, okay. And of course, distortion can also introduce a delay, okay, that is independent of the delay on the transmission line, because the actual point at which the signal crosses from a 0 to a 1 may change depending on what the loading of it is and how the signal behaves at the destination, okay. But, so here's an example, but we'll see later in the course, sorry, isn't it? We'll see later in the course that we can design systems correctly, okay, so that at some destination receiver we can actually have a nice clean square wave, okay, that resembles something of a square wave, okay, but by choosing the correct components and doing certain things, okay. But you can see at this point, at the beginning of the transmission line, okay, you can see that we have these other effects. We have these little peaks here, okay, so those sort of things might having terrible troubles with this Microsoft PowerPoint, okay, so these things would actually cause errors if that was at a receiver, okay, because the actual signal might be interpreted as, a 0, then a 1, then a 0, then a 1 again, okay, instead of just a clean transition from 0 to 1, okay. So we'll look at that more in the course, okay. So signal integrity is a term generally used for the impact that physical connection has on the transfer of signals from a source device to a destination device, okay. And actually, if you do end up designing, complex or fast digital systems, that will be one of your big challenges, to actually be able to transmit, signals around the printed circuit board and have them arrive at destinations in a correct format, and also not cause electromagnetic interference to other equipment, okay. So the analysis of signals, voltage, currents, in the case we rely on circuit theory plus a suitable model for the interconnect, which is a transmission line, okay? So we'll show that later in the course. Typically use a 2-port model, okay? It also, as I just said, has effects on electromagnetic compatibility, okay? Because if you have a lot of these ringing effects, then you can get a lot of radiation emitted from the circuits. In the end, all signals are analog, okay? So we look at a particular digital signal, a clock, okay? So a clock signal generally just goes from, repeats 0 to 1, 0 to 1, okay, to actually provide timing for a digital system, okay? And we have 2 aspects to it. We have the rise and a fall time, which is measured by this value tau, okay, and we also have the period of the clock, okay. So we can do the Fourier transform of that, okay, and we're going to have spectral components at discrete frequencies, okay, which are going to be, frequencies going to be f equals n on t, okay, but the envelope of these spectral components, you'll find, will have something of this form, okay, if you went and did it. Okay, we can look at that spectral envelope. So you have the discrete frequencies in here, but that the magnitude is bounded by this particular black line, okay, which is the spectral envelope. So you can see up to, in this case, t is 1 microsecond or something like that, okay, up to the fundamental frequency, okay, it's pretty flat, okay, up to the fundamental frequency of the signal, okay, so the period t of the clock, okay, then it starts dropping off, I think about 20 dB per decade, and then when we get up to basically that a frequency related to that tau, the rise or fall time, it starts falling off very quickly, okay? So if we look at that here, we can see we have the flat spectral envelope up to something relating to the period, then it drops off at 20 dB per decade, and then we start having a rapid fall off due after you pass a point that's related to the rise or fall time of the signal, okay? Okay, and notice that this is not related to the clock rate, okay? Okay, so when we are interested in you know, what is the frequency of the signal that is of, you know, the highest frequency signal of interest in a particular circuit, which is going to tell us whether our system's distributed or is not, or lumped, then it may not be the actual clock rate of the actual of the digital system. It's actually related to the rise and fall times, okay? Okay, so, you know, even if you had a system processing at 1 hertz, but if the rise and fall times are the order of 100 picoseconds, and that can be true, okay, then, you know, you really have to consider frequencies up into the gigahertz range, okay? Okay, so, you know, it's important to note that you know, digital, particularly digital systems, okay, it's really the rise and fall times of the actual digital signals that determine the highest frequency of operation, not the actual fundamental clock rate, okay? And generally, chip manufacturers want to make their chips as fast as possible, so those rise and fall times are generally pretty small, okay? So keep that in mind. Okay, analog systems. Generally, if we have analog systems, we're talking about narrow band signals, okay? So it may be at low frequency, like audio, okay? But could also be at high frequencies, like RF or IF, but just in a small range of frequencies around a carrier frequency, okay? Small signals, we may have distributed system effects, coherent signals. At low frequency, you might have large signals as well, okay? For instance, power, okay? But we generally want high linearity for small signals, okay? For digital systems, generally it's always broadband signals, okay? Because the information bandwidth goes from, you know, 0 to whatever the clock frequency is, okay? Okay. The clocks can be high speed as well, from hertz to gigahertz, and if you have fast rise and fall times, that's also introduces a lot of very high frequencies, okay? And it's large signal, okay? So, you know, that's the difference between analog and digital, is that we're always talking about large signal behaviour in digital circuits, okay? Because it's also non-linear, okay? That's why digital systems work, okay? They have some non-linearity that does this mapping from the input to a restricted output range. It's effectively a regeneration, and it's a non-linear effect, okay? So it's always have large signal behaviour, okay? Okay, for the analysis of analog behaviour, electrical circuit theory is widely applicable. Okay, and we use the application of circuit theory which requires the calculation of VI relationships at the terminals of every physical circuit element, okay? And we can use different things to actually get those models, okay? So I was talking more what I said earlier about, you know, abstraction and making models. You just want to get the bare essentials for the purpose at hand, okay? The usefulness depends on the adequacy of the predictions. So also, when you actually come to do designs, you're probably going to use computer-aided systems to do the design, but in general, you may want to do a manual analysis of smaller, more simplified systems, okay, to make approximations to actually see effects, okay, to understand how things operate, how you can adjust things to get the desired output, okay. So they offer insight into the effects of system parameters, okay, and how things are working and how you can design them to be better, or whatever you're required to do, okay. So some of the computational methods we use for circuit analysis, SPICE, LT SPICE or P SPICE, okay. For electromagnetic theory, there's a number of different approaches. One we actually model the electromagnetic fields directly in the time domain. It's called finite difference time domain. It's a very useful one. You have other ones that actually solve for the electromagnetic modes of structures, okay? We won't go into that in this particular course, okay? But we will be using SPICE for the circuit theory part, okay? And for digital, you have a lot of design languages that you use to characterize and capture and simulate digital systems, okay? And MATLAB, also these sort of things, you'll use that in the project in the second half, in the project in the second half of the course, okay? So I inherited all these notes from Tony, and he's very big on these, theory versus practice sort of words of wisdom. So if you want to read those, you can, okay? So it's a good one from Leonardo da Vinci. All sciences are vain and full of errors, are not born of experience, okay? But you also need the theory, okay? He who loves practice without theory is like a sailor who boards a ship without a rudder and compass and never knows where he may cast. So maybe you want to bear those in mind, okay? Okay, so that was a bit nebulous. That's the introduction to modelling, I suppose. What we'll do now is just try and finish off we'll try and have a bit of a recap of what you might have learnt in 3021. So if people haven't done 3021, I know there's a few here, there is up on the LMS all the course notes in the first half of 3021, which you can revise, okay, plus the tutorials. Okay, so, oops. So, if you're having any problems, perhaps look at that first, okay? Okay, so we'll look at these things: analysis domains, example of simple one-port elements, and examples of complex one-port elements, example of two-port elements. Okay, so classical network circuit theory is based on Kirchhoff's voltage laws and Kirchhoff's currents laws. Okay, it's a self-contained mathematical axiomatic theory for dimensionless networks, so something that has no size. Okay? Okay, and we have these four axioms. Oops. And Maxwell's theory is what we're going to do in the second part. Okay, it's also a self-contained abstract mathematical theory. Okay, and it's based on spaces that contain some materials. Okay, and electrical charge flows, electrical charge distributions. Okay, and it actually works with the aid of the mathematical concept of fields. Okay, so we invent these things called fields, magnetic fields and electric fields. Okay, and through them, okay, how they interact with objects allows us to make predictions, okay, and model behaviour of what happens in the real world, okay. Okay. So a network is defined as a system of interconnected network elements. Initially, we're just going to look at elements of one port, okay, and each network element has a pair of terminals that constitute the element port. Okay, each port has associated with two directed variables in specific direction conventions. Okay, so it looks like this. So a network element, which could be a resistor, capacitor, or inductor, or something like that, has two directed variables. So from before, what do you call this variable V or T? It's called the, from last year? Rise variable. What else? Sorry? Anything? Potential difference, right? Okay. So it's potential difference, okay? And it's measured in volts. It's not specifically the voltage, okay? The voltage could be other things, okay? But in circuit theory, we deal with potential difference, okay? Only, okay? We'll see that in the second half, right? We'll see things that they also generate a voltage, okay? But they're not potential difference, and they don't belong to circuit theory. But in circuit theory, it's all about potential difference, okay? Okay, and we have the flow variable, which is the current, okay? And the big thing is that current in equals current out, okay? Well, the magnitude of this going in equals the magnitude going out. So it's just two variables associated with an element, okay? That's an important concept, okay? And that's related to the fact that, it's dimensionless, okay? So if you put current in, then the same current comes out. If it was too big, then that wouldn't be possible, right? Because you'd have the speed of light. Wouldn't allow that to happen, okay? There'd be some delay. It can't happen. Okay. Okay, the only attributes that exist in the network are the directional variables associated with each element. Lines that describe the interconnection among elements do not have any attributes, okay? They don't have any length, don't have any direction, orientation. So the first axiom of circuit theory is elements described only by the two directed variables, okay? Which is seen, the rise, which is electrical potential difference, measured in volts, and the flow variable, which is electrical current in ampere, okay? Have the ideal wire. We have axiom 2, says the relationship between the two variables is assumed to be a characteristic of the element independent of all of other elements in the network in which it may be connected, okay? It can be linear or non-linear, okay? So it means that if you measure an element, okay, you find its VI relationship, you can put it in the network and you don't have to worry anymore. You've got a perfect description. You know that V and I, that's how they're going to be related at those terminals, okay? Okay. And we had two more network axioms, okay? Axiom 3, assumption is a zero-sum vertex flow, or which is basically Kirchhoff's current law. For every node in the network, the sum of inward direct flow variables minus sum of outward direct flow variables is 0, okay? That's KCL. And we have axiom 4, zero-sum loop rise, okay? So if you have any closed loop in the network, the sum of clockwise directed rise variables minus sum of counterclockwise directed rise variables is 0, okay? So that's Kirchhoff's voltage law. So the 4 axioms for circuit theory, okay? Okay, we can also have, so last year we looked at just 2-terminal and also 2-port devices. We also might have multi-terminal elements, okay? So, you might need that to represent dependent sources or, coupling among electrical components or subsystems. A lot of this time, these things where you want to have some multi-terminal, multi-port description or something, it's a bit like in software when you have a function, right? You really don't want to know how it works underneath, but you just want to instance, something that does that, okay? So, we may not be interested in all the details of the circuit underneath, but we just want some mathematical description of the relationship of the currents and voltages at the different terminals, okay? So that we can use that to design something or as a part of a bigger system. Okay. So for a multi-terminal element, we have, these terminals, okay, and we have these currents going into them. And the assumption is, okay, is that the sum of all the currents going in is equal to 0, okay? That's for a multi-terminal element, okay? So, for instance, you had a circuit perhaps like this. You might have, a transformer here that has coupling between it, has magnetic coupling, also has some capacitive coupling, okay? You want to put a wrapper around that, you might want to make that a two-port element, okay? But, if we were to look at the larger circuit, okay, there's all these coupling interactions between them, okay? And you might just be interested in, what happens at the terminals, okay? So then you might want to put that in a box and have a description of it that, just describes, how the currents and voltages at these terminals interact, okay? Okay. We don't have to conceal the detail. Okay, so the other thing is a multi-port element, okay? So you have a multi-terminal, you also have multi-port, okay? So, you often get that in electrical systems, is where you have networks where terminals are paired, okay? So, like a resistor capacitor, that's a pair of terminals. The transformer is another example. You have two terminals at the input and two terminals at the output, okay? So they're paired, and a pair of terminals constitutes a port, okay? Remember we said that for the port, the current in must equal to current out, okay? So I suppose you consider a multi-port a sort of restricted version of the multi-terminal one, okay? So obviously you've got to have an even number of terminals to make a multi-port, okay? And the extra condition or assumption is that the sum of the currents at each of the ports is going to be 0. So the current in here equals the current out, okay? So, the magnitudes equal, but directions are opposite for each of the ports, okay? So that's what we have, okay? In particular, two ports, we use them a lot at high frequency to describe circuits. Okay. So example of multi-port might be this transmission power distribution system that we were talking about before, where you have, each of these components, either the power supply where it's connected to a capacitor or something, is effectively a two-port, is a single port between ground and VCC, or the actual power supply, positive ground. Okay. And coupled inductors. Okay, you may have these effectively coupled inductors which form some kind of complex transformer. Then it would be a K-port element, okay? So looking at quickly going over the different modelling domains, okay? So far we've been looking at the VI characteristics in the time domain, okay? So the time domain is the root domain, okay? Okay, so that's the most basic domain in which we do analysis, okay? And all other domains are derived from this domain, okay? So what are the other domains that we use in circuit analysis? Anyone remember from last year? Yeah, okay, that's right. The Laplace domain and the frequency domain, okay? Okay, so in the time domain, we can do transient, steady-state analysis, linear and nonlinear, okay? In the Laplace domain, we can do transient, steady-state analysis, but it has to be linear. In the frequency domain, we can just do steady-state sinusoidal analysis only, okay? And it should be linear, okay? Okay, and for some electrical components, you may not have a good time domain description. It may be that the manufacturer will give you some VI relationship specified in the frequency domain, okay, in terms of some complex admittance or impedance, okay, it will be a function of frequency. So, transistors, capacitors, inductors, lossy lines. We've already seen a few, okay. Remember earlier on, we're looking at those high frequency ferrite beads and also capacitors. The actual manufacturer gave you a characterization in terms of frequency response, okay? Okay, so when you have that, then there's some limitations. You're only looking at steady state response to sinusoidal sources, okay? You can do superposition, okay, in the frequency domain, but only if all sources have the same frequency. We can do superposition at other frequency, but what do we got to do? Remember this from last year? You've got to convert back to the time domain, okay? So you have to find the result for one frequency, then convert back to the time domain. Do that for another frequency, convert to the time domain, add the results together, okay? Okay. So if we look at revising one-port linear elements, okay, both the time and Laplace domain, we have a resistor. It's my simple one. We have a capacitor, okay. So in the time domain, it's given by this differential equation, also given by this integral equation, okay. And remember, in the Laplace domain, okay, that capacitor is modelled by one on SC, but also the initial condition, okay? So also a voltage source in this particular case, okay? Or a current source, okay? So, okay, they come from the initial conditions, which come from here, okay? So that's what you can do in the Laplace domain. You can't do that in the frequency domain, but in the Laplace domain you can include initial conditions. The inductor, again, okay, in the time domain it's just a simple differential equation. The integral form captures the initial conditions, okay, but in the Laplace domain we always have the initial conditions there, okay. Okay, nonlinear elements, diodes, won't be worried too much about that. So in the Laplace domain, the representation of an inductor could be something like this. So the actual inductor plus a current source, which is related to the initial conditions, okay? And the capacitor is capacitor plus a voltage, okay? A voltage source which is related to the initial conditions, okay? So if you're given a Laplace domain circuit representation of a circuit, it means that circuit is, because it's linear, okay? If it's not linear, you can't have the Laplace domain description, okay? And it means that you can transfer all elements in time domain to the Laplace domain. Okay, the Laplace domain solution for any circuit potential difference or variable or current variable can be obtained by finding the solution for one source applied at a time and adding them, okay? So you can use superposition in the Laplace domain, okay? It doesn't have to be at a particular frequency, okay? It's because Laplace domain variables are complex functions defined over the S-plane, but the frequency domain variables are just complex numbers, okay? So it's a difference, okay? There's more information in the Laplace domain, okay, than frequency domain. So we'll skip this. A couple of inductors we'll actually go through in the second part of the course, actually deriving all these constants from electromagnetic theory, okay? Okay, so this is a description of a transformer, how the voltages at one particular port and currents are related to the mutual inductance, which is just L, the inductance of this particular coil, and the self-inductance, and the mutual inductance M, which is the inductance between the two coils. Okay, and you have end up with these relationships. Two-port examples, ideal control sources. Okay. Two-port models, we'll use this in the course as well. Okay, so if you're not familiar with it, please look at your notes from 3021. Okay, because we will be using two-port models. Okay, and particularly be interested in this transmission ABCD matrices. Okay, so so for the two-port admittance or Y matrix relates the currents, okay, at each port to the voltages, okay, and the impedance relates the voltages to the currents, and the transmission relates the VI at one port to the VI exiting another port. Okay, so you notice the change in signs here, because for the transmission matrix we're actually interested in not the current going in but the current coming out. Okay, so just the way that we define that. Sorry, come on. Just the way we define the different current directions, okay, and the conventions. Okay, something new. A transmission line. Okay, so this is a large distributed system. Okay, it can be any length, and but you have a port at the input, you have a port at the output. Okay, so we can actually model that in circuit theory with a two-port, and we do. Okay, and again, it's this ABCD matrix, transmission matrix. Okay, which relates what the voltage and current at one output port is to what it is at the input port. Okay, and we do that with a Laplace domain model. Okay, so it means once we have that model, we're going to show how we get that. Okay, you're going to do measurements in the lab as well. Once we have that model, that means that we can use circuit theory to describe circuits which have transmission lines in them. Okay, we do lots of different things, and we'll show, make approximations and be able to get some interesting results out. Okay, and the other thing is, we'll move on to that later, I think, that about the localization of different things. Okay, so that's what we'll be looking at a bit next, is how applicable circuit theory is to a particular circuit. Okay, so we can see here, if we had a circuit, okay, that was small with respect to the wavelength of the signals, located in this region, okay, then as long as this AB and CD are close together, okay, which they are, then there's no problems implying circuit theory to describe that. So even though we have a long delay here, we have a particular model for it, okay, that we can plug in, and we can use circuit theory to describe that system. Okay. Similarly here, we have even longer delay, and the actual transmission line stretched out over a large distance. Okay, but both terminals or both ports of the transmission line are close together, and the terminals are close together. So, and any circuit it's connected to is all close together, then we can apply circuit theory. Okay. In this case, we may have a circuit here, okay, and we may have another circuit here. Okay, so perhaps this is, you know, a sender and some receiver over here, and they could be separated by a large distance, right? But we can still apply circuit theory to the whole system as long as the only interconnection between the localised circuits at this side and the localised circuits at this side is through the transmission line, okay? If there's some other connection that isn't modelled by a transmission line or some correct representation, then we can't apply circuit theory. But if it's just if all the interconnections between components are localised, okay, between the ports are localised, then we can apply circuit theory, okay?
How do we define local?
If the distance between let's say the terminals of the port and the other network elements, okay, is small compared to the wavelength of the highest frequency signal of interest in that system, okay?
The distance between two points is really greater.
That's right. That's what I'm saying. This is from here to here. It's really big, right?
Yeah.
Okay, as big as you want, but you can still apply circuit theory because you have a two-port model.
But you say as long as it's smaller than the
Yeah, it doesn't matter. Yeah, that's true, right? That's true. But here, we actually create a model. Okay, we create some mathematical description of that. Okay. That's right. That's true. I mean, that's the thing. You see, we replace this with some mathematical model, okay, which we can use, okay, to predict everything. We can use circuit theory then, okay. Even if this actually predicts the delay, right?
So this one will even apply if it's not local.
As long as you can use circuit theory, providing you know, the actual terminals of any any port are localised, and anything other elements they're connected to via wires is localised as well. Okay, so perhaps we have some more examples. We'll go on to this. We'll go over it again. Probably. Well, you should know all this from last year, by the way. Bisection theorem, Miller's. Maybe it's not in this section. Here we are. We're talking about here. These are the examples we'll go through, right? So, you know, it's all about, you know, the distance between things, right? And so, yeah, you may have lots of one-port elements here, okay. As long as you know these things could be separated a large distance from each other, but you have a two-port description of that element, okay. That's applicable in circuit theory, okay. That actually describes V and I here, okay. It describes V